The purpose of this video is to continue with the second part of our discussion of the following paper, From Global to Local, an index bound for umbilic points on smooth convex surfaces, by myself and Wilhelm Klingenberg. Now, this video we will look at the reformulation of the main theorem, and here is that reformulation. It states that the index of an isolated complex point on a C2 plus alpha smooth Lagrangian section in TS2 is less than 4. Okay, so what we want to do is go through how we get this reformulation of the original theorem, which, if you recall, stated that the index of an isolated umbilic point on a C3 plus alpha smooth convex surface in R3 is less than 2. Okay, so let's try and work out how we get from there to this statement here. The essential role here of TS2 is as follows. If you look at the set of oriented lines in R3, and this means all lines in R3, not ones, for example, that just go through the origin. If you look at the set of oriented lines, it's not too hard to see that in fact this is the same as TS2. This can be seen in a number of different ways. The simplest way would be as follows. If you take an oriented line, say we call it gamma, and you want to describe such a line, well, there's two things that you need. You need its direction vector, which maybe we'll call u, and then we could look at the position of it as determined by the perpendicular distance vector from the origin. When we do that, then we can see that this is the set of all pairs of vectors u and v with the following constraints. Well, the length of u is not so important, it's the direction of this vector, so let's fix that to 1. And on the other hand, as we said, we want the perpendicular distance vector from the origin, so we want this dot product to be 0. Now, if we look at that, what we can do is we can take this u and we can move it to the origin. Suppose this is u placed at the origin, and if we take v and we move it so that, well, because this is a unit vector, it sits on the sphere, and then we can take v to the tip of that vector, so suppose that's your v, and because it's perpendicular, it's going to lie in the tangent space to the sphere. So you can see that every tangent vector to the sphere gives you a line, and vice versa, and hence we have this identification with TS2. Okay, so it turns out that TS2 has quite a lot of structure. In fact, TS2 of course has a projection onto the first factor, which would just take, for example, if we talk about it in terms of u and v, this would just map it to the direction of the line. But in fact it has a lot more structure. It has a complex structure. It's a 4-manifold. It has a complex structure. It has a symplectic structure, omega, and it also has a metric. These two together fit together to give you a Kähler metric, which we refer to here as G. Now, the important thing here somehow is the following theorem by myself and Wilhelm a number of years ago, which is that the isometry group, the connected component of the isometry group of the metric G here, is the same as the connected component of the isometry group of the Euclidean group. In other words, translations and rotations. So let's just say 3. SO3 or 3. What that means is that geometry here can be, in this metric in TS2, faithfully represents what goes on in the Euclidean setting. What's perhaps a little bit strange is the following fact, is that if you take the metric G, its in fact signature is 2,2. It's a 2,2 metric. It's what we refer to as a neutral metric. Now this is not the normal situation for a Kähler structure, so we often refer to this whole structure as a neutral Kähler manifold, 4-manifold. But it has many of the properties that are the same as the standard Kähler thing. It just has this somewhat unusual signature. Okay, so how then do we go about making this change from R3 to TS2? So the setting in R3, let's have a look at what we have. Well, what we have is a convex surface, and we have a point P on it, which is an isolated umbilic point. And what we do then is we translate this all into TS2, this four-dimensional space, as follows. In TS2, well, first of all, if you look at the oriented normals to this surface, these form a surface in the space of all oriented lines. So we normally call that sigma. What's more, if you take this point P here, and if you take that oriented line gamma, this will be a point here, gamma, and this gamma will be a complex point. In fact, it will be an isolated complex point. Moreover, because this surface, these lines come from a surface, this surface will be Lagrangian with respect to your symplectic structure. And again, here we'll see the difference why we have a neutral Kähler structure, simply because you couldn't have this in the definite situation. You couldn't have complex points on a Lagrangian surface in the standard Kähler setting. But in the neutral Kähler setting, such a thing is quite possible. In fact, it comes up just here. So let's maybe give a quick kind of dictionary back and forward between OR3 and TS2, the space of oriented lines. So the first thing is, of course, a point in TS2 corresponds to an oriented line in OR3. Right? So that's the definition. On the other hand, if you wanted to go the other way, it's not too hard to take a point here. Well, it's described by all the lines that pass through the point. So this would, in fact, give you a sphere. And this sphere, by the way, is holomorphic. It's a complex everywhere, and it's Lagrangian. Holomorphic Lagrangian sphere. Okay, what else? Well, if you have a convex surface here, surface S, how does that? Well, here, as we saw here, it gives you a surface. In fact, it gives you a little bit more. It gives you a Lagrangian surface. And what's more, because it can be parametrized by its direction of the normal, this can be parametrized by the S2. So it's, in fact, a Lagrangian section. What we might say also here is that you get a drop in differentiability. Of course, you're going to one derivative higher because you're looking at the normal line. So if you had a C3 plus alpha surface here, this would be a C2 plus alpha section. And this gives you the explanation of the differentiability drop that we get in our statement of our reformulation of the main theorem. As we said here, an umbilic point here means that the oriented line is a complex point. And then the final thing that we need to be happy with this reformulation is the following: is if we have an index here of your umbilic point, we've talked about that in previous video, here there's also a notion of a index for an isolated complex point, and the relationship is that this index is just 1/2 of this index. So 1/2 of the complex index of the point is exactly the umbilic index. So we have two different indices. I denote them with a small I and a capital I: umbilic index and complex index, just to keep them separate. Okay, so one further point that's worth making is we already mentioned if you had a sphere, right? If you had an S was closed, a closed surface, and isolated umbilic points, the sum of the indices should be the Euler characteristic. The indices of the isolated umbilic points should be the Euler characteristic, which is 2. Now there is this is all in OR3. In TS2, or in fact in any complex manifold, there is Lie's formulae, which says the following: if you add up all the complex indices over complex points, what you get is the Euler characteristic of your surface, whatever your surface is, plus the Euler characteristic of the normal bundle, because your normal bundle is, it's codimension 2 here, so tangent and normal, if you like, split up like that. So this is what's called Lie's formula. You can go further if your surface happens to be Lagrangian, as it is with us. Of course, then you have an isomorphism between tangent and normal in exactly the same way as you in the definite case. So the Euler characteristic of this is the same, in fact, as that of the normal. This comes in later. This form comes in later. So if you look at the sum over complex points in the case that we're looking at, where S is a sphere, or your sigma is a sphere, what you're going to get is 2 plus 2, which is 4, which is exactly twice the sum of the umbilic indices of the associated surface. So here we just see it all fits together. This factor of 2 comes in here because of this extra normal bundle factor that we arises in Lie's formula. Okay, so at this point then, hopefully we've convinced you that the main theorem to do with umbilic points and the index of umbilic points is equivalent to this reformulation in terms of the index of complex points on these Lagrangian sections in TS2. In the next video we will go on to talk about how we actually prove the theorem, in particular our method of totally real blow-up.